So even though you say, okay, nuclear energy, you want to have energy security, it's actually worse than oil.
So the first unit is always the most expensive, least predictable on schedule. So this implies risk for the developers, for the investors.
And the funny part is that right now, today, or in this year, 2026, 0.7% of the world's energy use goes towards all data centers. So it's still less than 1% of global energy that is being used by data centers. I know that it's growing very fast, and in particular in some countries, for example, US, it's growing really fast. But it will still be a number of years before it's 2% or 5% of global energy.
Somewhere outside Copenhagen right now, there's a company trying to build nuclear reactors the way you'd build cars. One day, off an assembly line, each one small enough to fit inside a shipping container. The technology is called thorium molten salt reactor. If that phrase means nothing to you, you're not alone. It meant nothing to most of the nuclear industry either, for the better part of 60 years. Today, we will talk about what it actually takes for a brand new reactor to go from design and a prototype to something that a utility or an industrial plant can buy, and why the traditional buyers that we have seen so far, data centers, are not necessarily the target customer. It would be more of a steel mill, for example. I'm Sylvia Leyva Martinez, and this is Interchange Recharged, the Mackenzie podcast where we explore how innovation, finance, and policy intersect to shape the global energy transition. My guest today is Thomas Jam Pedersen, co-founder and CEO of Copenhagen Atomics. The story starts more than a decade ago with a small group of engineers meeting up over beers in Copenhagen to talk about nuclear reactor technology that nobody else was building. Today, that's grown into a company with a large production facility outside Copenhagen and a new office in Switzerland. Thomas, welcome to Interchange Recharged.
Thank you very much.
So let's start with the question that I think a lot of the audience will be asking. So there is no shortage of advanced reactor companies right now. So most of them are still working with some version of water as a coolant, and you picked thorium and molten salt, which is a combination that is much less common. So why that specifically, and why does that is actually working better than a conventional design?
Yeah, so, I mean, we humans, we figured out nuclear energy about 70 years ago, and we've more or less, all the reactors we've built ever since is called light water reactors. It's sort of solid fuel reactors. There's some variations, but they're more or less the same, all of them, and the performance in all of these reactors are somewhat similar. But already back in the 50s, they saw that there was other reactors that you could build which had very different performance, 10 or 100 times better performance than these classical reactors. And many nuclear scientists have looked at this over the years, and nuclear engineers, and said, okay, I want to build these. But of course, it's a little bit more complicated to get started on a new type of reactor than what they used to be building. I usually compare this to radio tubes. I mean, we had radio tubes back in the 1900s and 1930s and so on. And then the transistor came along in the late 1940s. But it still took a couple of decades for the transistor to break through and sort of take over the market. And today we all have 1 billion transistors in our pocket. And I think this is the same. I mean, there was these old reactor types with water and solid fuel rods and so on. I think our type of reactor is the new thing that is going to take over. Much better performance, much better scalability, and so on. So yeah, it opens a new era for nuclear energy.
Perfect. This is awesome. And I remember when we were discussing in the prep call that the story on the origin of Copenhagen Atomics is quite particular, because usually when we think about nuclear or companies focusing on nuclear, is out of a lab or an R&D division with a bigger corporate player. So how was it exactly? Because that's quite interesting.
Yeah, so we were a number of mostly guys, engineers, and other people with technical interest meeting at cafes and bars and discussing nuclear energy. So you might know that Denmark is a country that has a history where half of the population were against nuclear, and we never got to build commercial nuclear power plants here. We only got sort of test reactors. But anyways, we were a number of people meeting up and discussing nuclear energy. And eventually it led to 2 companies starting out of that group of people. At some point, there was 100 people coming to these meetups and discussing nuclear energy. And it was basically, I mean, there was no national lab or research facility here doing nuclear research. But people are still interested in the technology and just it's just a random fact that people met in cafes and discussed this.
So it's more of a grassroots origin. I love it. and I also understand that the mission of the company is not only like having more clean energy, but it's also the cheapest, cleanest energy there. So tell me more about that.
Yeah, so I mean, there's a direct correlation between having access to energy and have prosperity in your country. And we see that all over the world, that the countries that have a lot of energy, they usually also have quite a lot of prosperity. And anybody, even the richest countries or even the people in the richest countries want to use more energy because it gives you a good life. And you are able to live a cleaner life and you're able to do recycling and so on when you have access to energy. So in the last 100 years, the total amount of energy production in the world has increased by a factor of 10. And we happen to believe, all the people behind this company happen to believe that because the whole world needs more energy, we will probably increase the total amount of energy production another factor of 10 over the next 100 years. And there's a huge opportunity to deliver that energy, but it needs to be cheap, otherwise people cannot afford it. I mean, there's 5 billion people who want to have more energy, but they have a hard time affording it even today.
Yes, and there have been a lot of discussions on affordability, particularly in the data center discussion. So we have seen that concern more and more. And energy has always been a political topic. I think it's more of a fact that people are more involved and the community in general is more aware of the cost of electricity, the different sources. So it's something that we're seeing in the world more and more. Okay, so let's jump now on the technology itself. So running this reactor at atmospheric pressure versus high pressure is one of the safety arguments that you led with. So tell me how it works in practice and how this goes beyond the theory, because I think that's a big change in the way we think about nuclear.
Yeah, so that's a little bit of an engineering truth. At any time in engineering, you want to build something that runs at high pressure, then it becomes more expensive and more complicated. And then if you mix in nuclear technologies or radiation, then it becomes even more expensive. So the combination of something radioactive and with a lot of regulations on top of something that is already under pressure, it just makes for expensive products. So we knew from the beginning that if we could make these reactors at atmospheric pressure, we could make them smaller and much lighter and less expensive, and also more available for mass manufacturing. So even before we started designing, we knew those engineering facts, and that has turned out to work really well for us because we've been able to make a reactor that is significantly lower cost and smaller size than all the sort of classical reactors, even the ones they call micro reactors or modular reactors or whatever. We're still smaller than many of those.
Oh, wow. So there is this component of the actual space, the cost, but also the safety. And one of the other things that I can think about when thinking about safety is waste. Nuclear and waste, like it's a very tricky conversation. And my understanding is that the design can actually run on some of it. So it's like a reactor fueled by recycled fuel. So how does that work, and what does that represent for the industry's waste problem?
Yeah, I just want to explain a little bit what waste is, because a lot of times there's many misunderstandings around this. So radioactive waste can have many different forms, and some of it is super radioactive, so very high radiation, and you can die right away. Some other forms of radioactive waste are maybe not that radioactive, but it's radioactive for 1 million years. So depending on what the different waste form is, it's easy or difficult to handle. And the spent nuclear fuel rods from existing nuclear power plants, those are the types of waste that needs to be stored in deep geological storage if you cannot recycle it. But fortunately, I mean, people have known this since the 1960s, that it's possible to recycle nuclear waste. The only country who does it right now, sort of on a commercial scale, is France. There has been other countries doing it earlier, but it's too expensive right now with these traditional processes to recycle spent fuel. But we found a way to do that with molten salt. Again, molten salt is also being used for recycling spent fuel. And also because our reactor uses it much more efficiently than any other reactor ever built, we can actually afford to pay for it. So first of all, there is a method to split it out of the existing old reactor fuel, but there's also now a possibility that we will actually pay for it instead of countries having to pay lots of money to put it in deep geological storage. And in our reactor, we can get roughly 10 times more energy out of those fuel rods than the amount of energy that were made in the first reactor. So imagine a country like, I don't know, USA or Germany or Sweden or whatever, that already have a lot of these spent nuclear fuel rods sitting around that they want to get rid of. Now suddenly they can make 10 times more energy than what they did throughout all those years with their existing nuclear power plants without digging any new fuel out of the ground. That's not entirely true. You need to mix it with thorium. So you still need to add thorium to the reactor to achieve this high burn-up.
And how does the supply compare versus uranium or the typical fuels that are used?
Yeah, so the way we came to this price that we're willing to pay $10,000 per kilogram, that's actually related to what is the current cost of uranium. So if we pay $10,000 per kilogram for transuranics, then we will end up with roughly the same electricity price as if we were buying fresh uranium out of the ground, and also that needs to be enriched if we use that instead. So it's great that we have a reactor that can either run on uranium or spent fuel.
Yes, definitely. And when thinking about the availability of resources in general, this is one of the main topics that we have discussed on the show. Nuclear, not necessarily just because we have not had that many guests covering this technology, but in general about the need for rare materials, for like metals needed to build data centers, to build modules. So the resource conversation is crucial to understand and to find different solutions, which is one of the ones that you're proposing. Where does testing of these reactors standing today? Because we have seen a lot of different projects and proposals of new technologies. So it would be interesting to hear what has been proven and what's still ahead.
At our current facility here in Copenhagen, we are able to test these reactors and as what is called non-fission prototypes. That means that they were not allowed to start the chain reaction here, but we can heat them up with electricity and do a lot of the mechanical testing that needs to happen before we can have commercial reactors. And then we are planning to run the first reactor with chain reactions in a national lab in Switzerland. That national lab is called PSI. So that's sort of our first testing that will be ongoing. So we've already run lots and lots of testing on molten salt and made sure that pumps and valves and corrosion and other things are working as it should. And now we're testing on full-scale prototypes that are the same size as a commercial reactor. And eventually we will run one of those also as a test in Switzerland. And then from there on, we need to go towards commercial reactors. And then there's not a lot of testing or uncertainty. Then it's mostly all the licensing process. The licensing process to get a commercial reactor, especially a new type of commercial reactor, is quite extensive.
Perfect. Love it. You mentioned it earlier in the conversation that we are expecting that energy demand will continue increasing by tenfold by 2100. So what is the case there? What role is these new technology playing, and why isn't just continue to develop conventional nuclear a solution to achieve to meet the new levels of demand that we're expecting over the next few decades?
Yeah, that's a good discussion that many engineers are having, and I guess scientists as well. I've debated people many times. How much can we scale the existing energy technologies, not only nuclear but also coal and oil and gas and wind and solar and hydro. Of course, I mean everybody knows that hydro is one of the energy technologies that does not scale very much more than what we've done already. Maybe in a radical situation we can double hydro, but so that definitely doesn't scale 10x. And then we can talk about coal and oil and gas. I think oil and gas could easily double, but if you want to triple them, maybe it becomes difficult. I think coal, maybe you could make 5 times as much energy from coal, but people don't like coal, especially in the Western countries. And then nuclear, the traditional nuclear, you can probably, in the next 100 years, you could probably make 5 times as much energy from traditional nuclear. But, today it only provides 5% of global energy. So even if you make 5 times more, it doesn't really make a big difference.
Yes.
And wind and solar, wind and solar could probably increase by a factor of 10 or 20. But again, also, even if you increase wind and solar by a factor of 10 or 20, it doesn't provide enough energy. So my conclusion was many years, this is 20 years ago, conclusion was that the energy technologies we're using today is just not able to scale to 10x. We need to invent something else. And for many years, I looked towards fusion. I thought fusion was the solution. But then I came across this thorium energy, and I think thorium energy can scale much better than fusion. And I would actually say that thorium energy is the only energy source we know of that could scale 100x from the total amount of energy we use today. And this is wild. This is something that most people cannot even imagine if we had 100 times more energy. So basically, that would be 100 times more than all energy companies in the entire world today. So that's a huge amount of energy. And if we get there someday, I will be dead by then. But if we get there someday, of course, thorium would be providing almost all energy.
Oh, wow. Wow. And I think the only challenge that I have there, and it's a discussion that I had with Maria Korsnick, president of the Nuclear Energy Institute, in one of my first episodes at Host, because it seems that nuclear technology always has this challenge of being first of a kind, particularly like new technologies that are being developed. So the first unit is always the most expensive, least predictable on schedule. So this implies risk for the developers, for the investors. So how are you thinking about that risk for your own first reactors?
Yeah, you're absolutely right. For any type of product, even if you make a bicycle or a car or whatever, it's also difficult to make the first of a kind of a new type. And that's also true for nuclear, but especially for nuclear, it's very expensive to get the licenses. And also, so our reactor is actually not that expensive. It's quite small and therefore not expensive to make the hardware for the first one. But most other nuclear companies, the very first reactor is going to cost like $1 billion, and it's very difficult for a small startup company to get $1 billion on something where you don't quite know if it's working. But in our case, the reactors are much less expensive, sort of in the order of $6 to $10 million, not $1 billion. So we can easily build a number of those reactor units. We've already built a number here, and we're expecting to build at least 20 units before we have commercial reactors. So in that sense, we are very different from other reactor companies. But of course, we still need the nuclear license, and that's still super expensive.
Yep.
So that it is difficult to get investors to pay for that, because they ask what happens if we don't get the license. What happens if something goes wrong? And then basically the message is then the investor lose their money, and they don't like that message. And that's also why a lot of people think that nuclear technology can only be developed by governments, because you need somebody to underwrite the check that is willing to lose all the money. But I think for some of the biggest reactors, some of the old stuff, the big designs, probably you need governments to underwrite it, because it's so expensive. It's not only $1 billion, it's sometimes $20-30 billion. So for those, I don't think startup companies are going to make those. But these new type of reactors like ours, and also there's a few other companies who also make things that are not high pressure and therefore low cost. I think it's actually possible for startup companies to create those types of technologies. But you're right, it's a difficulty. It takes many years to go from you start the company until you have a commercial product. And it's difficult to raise all the money to keep the company going for all those years until you start making revenue. And in our company, we have solved that by actually already today selling components and salts and other technologies we've developed to sort of co-fund this long period of time before we have commercial reactor revenue.
So in a nutshell, is the design of the reactor itself helps because it's a lower upfront cost. So CapEx decreases and the order of magnitude of the investment is more manageable compared to a traditional reactor. Plus, the model of the company itself, it's also allowing to self-fund by diversifying and not only focusing on reactors, but other elements that could also be of interest for the industry, which is something that we're probably going to see more and more of in the technology side. And one other thing that I found fascinating was the business model itself, because it's something that I have not heard of before. So tell me more about like this dynamic of upfront cost and then like an annual fee for thermal units. So tell me more about those dynamics and what those numbers actually cover.
Yes, so we've had a lot of discussions with different potential customers, and of course, not every customer is the same. But we found out that most customers, they want to start with some small power plant, and then once they see it's working, then they want to be able to add more and more units to make it bigger and produce more energy, which is that's a way for the power plant owner to reduce risk. And then another thing we saw is that they are really focusing on cost. And in countries like India, for example, they want to manufacture as much of the power plant in India as possible. And it's not only India, but that's just a good example. There's many other countries where it's the same. So they want to manufacture as much as possible in the local country. And therefore, we came out with this business model where most of the power plant, that means all the steam turbines, all the buildings, all the connection to the grid, all the sort of things that are not related to the reactor design itself, that is responsible of the power plant developer or the power plant owner. And they can source that locally or from any supplier they like. If they're from Russia, they can buy it in Russia, whatever. And then the reactor unit itself, which is the unique technology, that is the thing that we provide. That's sort of the heart of the nuclear power plant. And you don't need to buy 20 or 30 units in one go. You can buy one or two. And then once you see that they're working well, then you can add more and more units to your power plant. And this also allows us to mass manufacture these units. And we can sort of sell them, all units are exactly the same size, the same color, everything. And this means we can mass manufacture it, and we can focus on improving that technology, the reactor technology itself. And because our reactors are very dependent on the fuel quality is super important for the performance of the reactor. So we also supply the fuel. So the model is that we supply the fuel and the reactor unit, and then the power plant owner supply all the rest, which is essentially 75% of the power plant cost is all these other things. And then they can scale out as they want. And this, when we did the calculation, we came up with a business model where we take $50 million up front. That's for us to get started in manufacturing the unit. And then once we deliver the unit, then they pay $2 million per year to keep it running and keep it fueled. So as long as they want to run it, if it's 10 years or 20 years or 50 years, then you just keep on paying $2 million per year per unit to, basically. Then we help them keep it running. And I think that's a good model both for us and for them. It's a little bit like Intel inside, all these computers where it says there's an Intel chip inside. That's a little bit the same here. That you will see a power plant and then it says Copenhagen Atomics inside, something like that.
And I think it also some things to highlight is like on one side is the standardization. So you mentioned it's modular and all components are the same. So it doesn't matter where you install it. The actual reactor is going to be the same rather than this more complex ad hoc design that takes more time, takes more resources to design and implement. So I find that really fascinating. And the other part to mention is about 75% of the cost being everything else aside from the reactor, because that then puts pressure on utilities, on IPPs, I need to optimize everything else because the technology, the reactor itself, is not the major cost component. So that puts more pressure on them, on regulators with getting licenses, interconnections, stuff like that. So it's a very interesting way to think about how these dynamics are working. Is not the technology in isolation, is how it interacts with all the different players in the market. This takes me to another point related to like this interaction mainly with utilities in the example that you mentioned. So tell me why this model exactly like makes a difference on how utilities and IPPs are thinking on the way they procure their power, and also how is it different from what we have seen so far on conventional nuclear?
Yeah, so I know later on we're also going to talk about data centers, and I want to start this a little bit now. So there's different types of customers in the market that are willing to pay different prices for electricity. And something like a data center, they have a very high requirement on the availability. So whenever they turn up their CPUs or their computers, they want to be able to get more energy right away. So they want a very responsive delivery system, and performance of the delivery of electricity is of high importance, but they're also willing to pay a higher price. Whereas there's some other industries where good examples are production of steel or production of aluminum. Those types of industries, a very big part of the final product is the energy cost. And they are very, very focused on getting the energy cost down all the time. So they have a different offtake. They are very focused on price. And so depending on who your customer is, there's a different price point that is important. And we focus on making very efficient reactors and very low cost energy. So we will likely go after the type of customers where price is the most important thing. We can, of course, also sell our reactors to data centers, but in those applications, we have many more competitors because right now everybody wants to sell to data centers. And the funny part is that right now, today, or in this year, 2026, only 0.7% of the world's energy use goes towards all data centers. So it's still less than 1% of global energy that is being used by data centers. I know that it's growing very fast, and in particular in some countries, for example, US, it's growing really fast. But it will still be a number of years before it's 2% or 5% of global energy. So of course, there's still other type of customers that are much bigger. And in the end, the majority of all electricity is sold to the grid. And then, when it goes on the grid, then it goes to all kinds of customers and private individuals. So I think for the majority of our customers will be power plants that deliver electricity to the grid.
Yeah, and let's touch on that because so data centers are not the main target off takers. So I would assume then it's more on the heavy end industry side. And I think there's also a component related to the load profiles for one versus the other, because data centers, one of the main challenges that we have seen is like these peaks of power, these needs for very quick ramp ups, ramp downs. And there are other companies like on the manufacturing side still also has some peaks, but it's a bit more measured, more manageable, aluminum production and so on. So can you tell me more about like those nuances and like why the double down on not focusing on data center right now, aside from the demand perspective?
Yeah, so the type of customers who have a very high focus on price, they will look at the whole year of production and look at the price that they can get if they sell the electricity to the grid. And in some cases, if you sell electricity to the grid 10% of the hours of the year where the price in the grid is the highest, then you can make some or almost like 40 or 50% of the revenue from the year in just those 10% of the hours. And of course, if you have an aluminum plant that needs lots of power, then what you want to do is you want to sort of close down your aluminum plant in those hours where you can sell at a very high price to the grid. And then you want to run your aluminum plant in all the other hours where the price is quite low. And this is a way to lower the cost of energy for aluminum manufacturers. But a data center would never do that, because for a data center, the cost of electricity is not the main cost. I mean, the main cost is all these GPUs and the infrastructure. And they need to pay the interest rate or pay that off anyways, all hours of the day.
Yeah. And I've been thinking of one other element that I discussed previously on the show, and data centers and this expectation on new load has been driving the conversation a lot in terms of what is shaping the supply and the type of procurement that we're expecting over the next few years. And in these conversations, it seems that nuclear, and this is part of some of the research that we have done at WoodMac, is that we should not be expecting any new nuclear before 2035. If the announced projects, most of them are like more on the conventional side, land on time and on budget. So why, like, do you agree with this view? Where do you think we're wrong? And what role does your technology play in all these conversations?
I do think we will see some nuclear power plants before 2035, but I think you should look at the global market of nuclear energy and say, at what point have we increased the total amount of nuclear energy in the world by 1% and by 5%? And yeah, even though I say we will see a few power plants online between now and 2035, I don't think we will not increase the total global nuclear production by 2%, but because also some of the power plants are coming offline. So it will be a tiny addition to the global system by 2035. And I think then beyond 2035, we will get more and more power plants up and running. And then probably by 2040, maybe we'll have increased the total energy production, nuclear energy production by 10 or 15%. But it will not be until, I don't know, I'm just guessing now, but 2045, maybe we can double the total amount of nuclear energy in the world. And then maybe 5 years later again, we can triple it. Because suddenly when we get there, more and more of these power plants that have been building for 10 years, they will be ready and they will come online. So when we get in the 2040s, I think every day you would hear about a new nuclear power plant that comes online, either from us or some of the other companies. But it is sort of, it's a difficult ball to start, getting it rolling. So exactly what you said. There will not be a lot of additional nuclear energy by 2035.
Perfect. That's useful to get a different view. And I think one thing and we touched on this earlier in the episode, was about how difficult it is to fund these projects. And that's one of the components contributing to having no new nuclear by 2035. And I wanted to ask about that, like from your perspective, because this is a capital intensive industry. You mentioned that there's competition from other technologies. So what does it actually take to finance a company like this? And what are the types of conversations that you're having with different players in the industry?
Yeah, so one thing is to fund all the R&D from investor money and VCs. That's sort of one particular part of the journey. A very different part of the journey is when you start to fund real power plants. But us as a company, we actually not involved in funding the power plant. That would be utilities and other companies owning big power plants. But if you think about it, so if you buy a new offshore oil drilling rig, I mean that can easily cost anywhere between $5 and $10 billion. So those systems also cost as much money as a nuclear power plant. And also, if you buy a new airport or a new hospital, I mean there's many other things in society that cost the same amount of money. And also, if you want to build a new airport or a new hospital, it also takes many years. I mean you need to find the financing, you need to find the area where you can build it, and you need to get all the approvals. So some of those big projects also take 5 or 10 years to build, especially an airport. I think it takes more than 10 years to get that financed and get all the approvals and build it. So it's not very different from nuclear power plants, I would say. But of course, there's a different risk in nuclear power plants because very few times you've heard about somebody building a big international airport right next to a big city, and then 5 years after it's open, they close it again. I've never heard about that. But you've heard about that with nuclear power plants. So they built this very expensive nuclear power plants, $20 billion, and then 5 years later, there's Greenpeace or something, get it closed down again. And this is something investors, they are really afraid of. Because if you invest all those money, it's supposed to, earn back the money over the next 50 years or whatever. But then if they close it down after 5 years, you're in big trouble. And that's part of the problem in nuclear, is that investors are quite cautious because of the history. I mean, what happened in the past, there was some bad examples. But I think 10 years or 15 years from now, hopefully investors have forgotten about all these old bad luck situations where government suddenly shut it down, and it will be more, or it will be perceived as less risky than what it is right now.
Just to add one data point, I'm originally from Mexico, and I was living in Mexico City by the time a new airport was announced. You probably heard the story. They started the construction and everything. A couple of years later, with the new administration, the airport was canceled. It never started working, but it was clear, like, the investment was already there. The contracts were already signed. So maybe you have one data point of reference related to an airport being canceled.
I didn't know about that, so... Thank you for sharing that. That's a good example of something that investors are afraid of.
Yeah, definitely. Other sources of uncertainty, not necessarily tied to projects like a new nuclear reactor, but just to show that things like that happen.
Another uncertainty is the fuel supply, because most nuclear reactors in the world, they need enriched uranium. And there's only very few countries in the world that produces enriched uranium. Of course, Russia, there's a few countries in Europe. US is now starting to make enriched uranium, in China as well, and a few more. But it's like two handfuls of countries in the world that makes enriched uranium, and that then you're sort of relying on them to supply uranium to you. So even though you say, okay, nuclear energy, you want to have energy security, it's actually worse than oil. The Strait of Hormuz, and also what happened with Germany and the gas. Those countries got in trouble because there was not sufficient supply. But with uranium, it could be even worse, because now if we want to build 3 times as much nuclear power in the world, maybe there will be a shortage of supply. And then if you build a big power plant, $20 billion, and suddenly the country that promised to sell you uranium no longer want to do it because they changed their president or whatever, that is a shitty situation. And this is also one of the reasons why you should buy thorium reactors, because there's thorium available in any country of the world, and you don't need enrichment. So it's a much more reliable energy source, and also it's not very expensive. So you could actually buy enough thorium for 100 years and put it in a pile.
If you're a utility, a financier, an off-taker, a government watching this space, which I know many of our audience are fall within one of these buckets, what should they be thinking about right now for this technology and for advanced nuclear more broadly?
I would say nuclear energy in general are definitely going to be a much bigger part of our global energy supply, and especially our type of energy, thorium energy, which is able to burn spent nuclear fuel and so on, and it's much more reliable type of energy and low cost. I think they should start educating themselves about it, and they can go to our website and learn more about it, or watch podcasts like this or YouTube videos to educate themselves about what are some of the opportunities that are coming within the next 10 years. And I'm 100% confident that this is going to revolutionize our entire energy system, sort of in the long term, let's say in 25 years from now.
Awesome. And one last question, and crystal ball question. What do you see the world looking like in 10, 20 years from now, and the role that nuclear is playing?
Yeah, nuclear is a little bit slow because of all these approvals. So it will grow slowly and become bigger and bigger. And I think by the time I'm an old guy, much older than now, nuclear energy will be our primary energy source on this planet, which right now it's coal and oil and gas that are the biggest suppliers of energy. So that's exciting for me to see that take over the next 20, 30, 40 years.
Amazing. Thomas, thank you so much for joining me today. This was a great conversation.
Thank you too, and thank you for having me.
And this was Thomas Jam Pedersen, co-founder and CEO of Copenhagen Atomics. Thank you so much for joining us. And to our audience, thank you so much for tuning in. You can find Wood Mackenzie's full nuclear energy transition research at woodmac.com. I'm Sylvia Leyva Martinez, and this has been Interchange Recharged. Thank you so much. Muchas gracias, and I'll see you in 2 weeks.